Okay, welcome back everybody. In the last video we were going through the notes and showing that by working out what the diffusion current in the bulk regions is, you can then actually work out what the current flow through the p-n junction is. And we found that for electrons you can calculate and should calculate what the drift and diffusion current is for both the n-type side and the p-type side, but what you actually find is that in the p-type side here, you get diffusion current dominating, whereas in the n-type side, you get drift current dominating. So drift current dominates, that's the one that we're all familiar with when there's an electric field, and you just calculate it using the majority carrier concentration, which is what we're really familiar with, the number of free carriers. The drift current though, the diffusion current becomes important, even though it's a minority carriers that are important when you're talking about electrons in the p-type side. And the reason that you can hopefully now see that they're important is because they form a concentration gradient when they're the minority carriers and a voltage is applied. And that's what's happened to electrons in the p side. And we've calculated that and even shown that even though they're minority carrier concentration, because there's a gradient present, it gives rise to a diffusion current. The diffusion current sets off this current flow from one region to another, and it's the diffusion current, and the calculation of the diffusion current is all you really need to do, because you can then calculate that that current is balanced out by the drift current as the electrons cross from the p side to the n side. So that's really what's going on in a p-n junction. Hopefully by now you have also actually done the calculations for the holes as well, and will have calculated that exactly the same thing happens for holes. And in the case of holes, you'll find that again, drift current dominates when holes are in the p-type side, in other words, when it's the majority carrier, whereas it's diffusion current dominated, the hole current is diffusion current dominated when they are in the n side. So again, the concentration gradient of holes will be established in this n region because of the bias that's been applied. That will cause the holes to flow, and the hole flow, in other words, the hole current, is simply balanced by the hole drift current on the p-type side. So I think that's quite interesting, and I hope clarifies how the current will flow across a junction when a bias is applied. And this is, as I said, particularly important to understand how bipolar transistors actually operate, because you're applying a bias to the two junctions in particular of the p-n junction, and you have to understand that the gradient that's set up will dictate how much current is then going to flow. Now that we know that, we also know that we have to combine the electron current and the hole current to estimate the size of the current flow through any p-n junction or any other device. And so we really need to start putting these two together, summing up the electron current flow and the hole current flow, because we want to establish the relationship between the current flow I or J, if you're looking at current density, and the voltage which is applied. We also know now that you don't really need to calculate what the drift current is in the region where it dominates, because in fact it's the same as the diffusion current. And so it's much more simple if we just think about the diffusion current, and therefore just think about this minority carrier concentration. And that's why those equations were so important. So we know, we're coming back to our schematic here again, that in a forward bias, we've established an increase in the minority carrier concentration in both the p-type region and the n-type region. And we get an increase at the edges of the depletion region, and we call the new minority carrier NP or PN for the n-type region. Those electrons are going to flow down the concentration gradient in the p-type side, and the holes are going to flow down the concentration gradient in the n-type side, and then go around. We also know that hole diffusion is in the n-type side when we calculate that, given by this equation, and we've used that to calculate what the actual value was previously. We're now changing it from a diffusion current density to an actual current. So we just put the A on the other side, and that's the cross-sectional area. So our diffusion current is the area times the charge times the diffusion coefficient times the concentration gradient of holes on the N-type side. That concentration, that dP, is we're still, even though we're in the N-type region, we're looking at hole flow, so we have to look at dP, which is the diffusion coefficient of holes, which comes about from the mobility of holes. And dP over dx is the change in the concentration gradient. So we're in the N-type side, and it goes from its maximum value Pn, which is up here, to its lowest value further away, which is its equilibrium value Pno. And we divide the distance is Lp, the length over which the carriers are going to travel. Exactly the same for the electron diffusion in the p-type side, and that is the electron current is given by the cross-sectional area times the charge on an electron times the diffusion coefficients for electrons. We get that from the mobility of electrons, but it's electrons, so we have to look at n, and the concentration gradients dn over dx, where dn is going from the maximum value np to the minimum value np0 further away. So we then divide that. The dx here is the distance over which the carriers travel, the electrons travel, which here you can see is ln, okay, the distance or the bulk dimensions. We also know from our equations 31a and 31b, which are repeated down here in your notes again, that you get a very large increase in this minority carrier concentration. Only one's printed on my sheet. You get a large increase in the minority carrier concentration when you apply this forward bias. It's exponentially dependent on this voltage VA. So this NP over NP naught is going to increase significantly when you apply a voltage. So you've got 31A and 31B, which is the same thing for holes. We want to substitute these into our equations 32 and 33 above. So going back here, this is just showing you the equation for the hole current and the electron current, 32 and 33. But we need to figure out what NP is and what PN is. But from equations 31A and 31B, we have that. We have an expression for NP. It's at the top there. And we have an expression for Pn. It's at the bottom here. So we simply substitute these expressions. We're just going to take it. So it's Pn equals Pn naught e to the e over kBt times Va. That's the Pn. And similarly, Np equals Np naught e over kBt times Va. So we're going to substitute these into equations 32 and 33. Okay, and then when you do that, you reach these equations 34 for electrons, 34A for electrons, I should say, and 34B for holes. So it looks a bit messy at the beginning, 34A, once you've done the substitution, as we have here, this equation here, NP equals NP naught, 31A has been substituted in here. And so we tidy it up because NP naught here and here can be taken out. It's a constant for a given doping concentration. So it's taken out here. These are all constants, the area, the diffusion coefficient, the electron just here, the distance of the bulk are constants. And now we're taking out NP naught as well, because that's also a constant. And you can see then that you've got an electron current which is related to a bunch of constants and then exponentially dependent on the applied voltage, -1. And hopefully this is now looking a little bit more like Shockley's equation. We do the same thing for the hole current, and you reach 34B, where you've got the hole current is dependent on loads of constants, which are design parameters, and particularly in forward bias dependent on the applied voltage, as you can see there. In fact, all of the constants that we've taken out, well, first of all, we have to remember that we have to sum up these equations, okay, because one's the electron current and one's the hole current, but they're both present when we're operating the device. So in fact, before I go on, we have to remember to sum them up. So this is I, which is IN, this is IN 34A, IB, IP 34B, that's 34A, IP is 34B. We add them together, we get this, still we get a list of constants and the dependence on the voltage. Now this part here is the same for IN and IP, so we can take it out, it's common. And then what we find is that we've got a bunch of constants that we have to multiply the voltage dependence by. And so we can define these constants as I0. We can define them as anything we like really, but I0 is really called the reverse saturation currents. And it's the value of the current that you see when the voltage is being applied, when a negative or a reverse bias is applied to the PN junction. So this is the value at which an ideal diode will saturate at. And what you can see is that it's dependent on design parameters, doping level, and your material choice, okay? So within that, you've got the area, well, that's what you design. You decide how big your device is going to be. The charge on an electron is constant. It's the diffusion coefficients for electrons and holes. Those are constants for a given material. Ln and Lp are constants. They are the length of the N and P type or the P and N type regions. And then you've got these values, NP0 and PN0. Well, those are the values, the equilibrium values for the electron and hole concentrations when they're the minority carriers. But that's just determined by the doping concentrations. And again, you decide what the doping concentration is. So everything within I0 is really just a design parameter. And that's why it's a constant. You can determine what that's going to be. You can also see, though, that this portion up here is showing you that this total current in forward bias is exponentially dependent on the applied voltage, VA. And that's why when you have these current graphs, you have a large increase in current as you increase your forward bias. And that was shown on the first page of your notes. So we simplify I0 and we get to equation 37. Here I0 you can now see has come from all of this stuff, and that is just a constant. And this is known as Shockley's equation, or sometimes known as the diode law. In real life, materials aren't perfect though, and they don't actually have this type of ideal equation. So this is known as an ideal diode law really, or an ideal diode equation. But actually what really happens is that you might get slightly less current out than the ideal situation. And because of that, we want to know how much less current, because we designed devices believing that a certain amount of current will come out with a certain applied voltage. And so we want to try and figure out what is the actual current that's going to come out. And so we need to use some sort of fiddle factor to try and understand this based on the material properties. And this fiddle factor is represented by this N here. And just note that this is not N, the concentration of electrons anywhere, it's just a fiddle factor. And in fact, in the ideal case, when diodes are operated as being determined by their minority carrier diffusion, as they ought to be, N is simply equal to 1. And that would be the perfect case, and that's why it's not been included in equation 37. But in reality, there's some recombination of the electrons and holes, which means the carrier concentrations are slightly different, and therefore N could head towards 2 and reduce the current that comes out. So we need to often calculate what the ideality factor is for the diode to see how good or bad the diode actually is. What are the material quality like, and how much recombination is really taking place? So under forward bias, we really see that there's a recombination current in addition to the diffusion current, and working out how close to 2 or the value of 1 or 2 it is tells you what's your sort of mechanism, and what are the problems with your device and your fabrication process. So that really brings me to the end of the Shockley equation and its derivation. But one other thing that does need to be taken into account when we're calculating or assuming that we can calculate the amount of current out for a given voltage is the diffusion length of carriers in the bulk and how far these carriers are going to go. So that's really moving on to perhaps this next small section. It's worth pointing out the diffusion length is the average distance, it shows here, it's the average distance the carrier travel before it recombines. So an electron will recombine with a hole eventually. And because of that, in fact, these holes which are sitting in the n-type region don't gradually decrease. In fact, they will, relatively quickly decrease, okay? They're not going to be a constant. So clearly, when we look at the diffusion length, we've taken it to be we've taken it to be the carriers will travel the length of the bulk. But in fact, that's only really true if the bulk distance is quite small. In fact, if the bulk distance is longer, in other words, the bulk length is longer than the diffusion length, you need to replace this distance of the bulk with this distance here, which we call which is related, in fact, to the diffusion length. And we can calculate that by knowing what the diffusivity and the diffusion coefficient is for the type of carriers, which will be dn for electrons, and the recombination time, which is usually in the range 10 to the minus 10 or 10 to the minus 8 seconds. So instead, for long or relatively large devices, which we do try to avoid, in general, things are getting smaller, we have to consider instead the diffusion length of diodes rather than simply how big the diodes are. So because of these curved profiles and the diffusion length, the derivation for the Shockley equation that we've been covering is that you'll notice is really quite simplified, perhaps compared with a realistic case where diffusion and the recombination needs to be considered. So as it says here, this makes the analysis a little bit more, well, considerably more complicated. But the main part of this section is for you really to understand where this analysis comes from, where the diode equation comes from, and some of the assumptions and approximations in getting to that simplified version of it. So that's all I really want to cover for now. And in the next section, I will talk to you again about perhaps why there's some difficulties with diodes, that you can't keep increasing the voltages on them, that you do get, if I just scroll up, you do get some slight deviations from this perfect diode schematic that I've scribbled here, and the one that you'll see on your front cover of the notes. So we've derived it, we've made approximations. This is a perfect situation. In reality, there's some recombination, and that gives rise to a slightly reduced current than you might expect, and slightly different breakdown characteristics that we'll cover in a moment.